Yeah, I feel like I vegged out too much then. Like it was too long and it just became.
You don't love the freaking
Yeah.
I was happy to have that though. I had so much to do just personal life wise, getting stuff together.
Yeah, I don't know what happened to my time. A baby ate it and then Halo ate the rest. That's about it. I remember.
The molar mass is just the grand scheme of the whole thing.
Yeah. Yeah, and then sometimes they like say atomic weight, formula weight. It's
Yeah,
I don't.
that seems to have a lot of names.
Yeah,
I don't remember what lesson it was, but I remember I was like, it was given a name that I had seen before. I'm like, what does this mean?
Yeah.
And I went through so much effort to find out. Oh, it's just the atomic weight. It's just the molar mass.
Yeah, and I don't get because they use all the abbreviations like FW, AW, MW. It's like, pick one.
What? Please.
There you go.
It's not my fault. Blame Andrew.
What?
We're blaming you. Because everybody except for Bree's gonna be gone on Thursday. So we're blaming you.
Blaming me because I don't see how this works. I am not the one who scheduled your appointment.
Yes, but you're the one choosing on me.
How dare I want a day off?
How dare.
There's a dude on the roof. Over there.
That'd be kind of frogs with their empty juice.
Frogs are impressive.
Just shove some frogs in my harness.
No, they got antifreeze proteins, antifreeze-like proteins in their blood.
Yeah.
I knew I think I don't want to.
He drank it.
Yeah, I think there's one that can
Yes. Yes. Exactly what he did.
Yeah, that's happened to me before. I walk up there and I'm like, oh, no. Farms and fries.
Yeah. And then we had food colour. Yeah. Yes. Yeah. Just go buy a bottle. Yeah. Go
I did finally rework work. And I'm officially
The more you drink, the more you can handle.
You did free. No, I did the entire body. I always feel like I'm high. Because I'm just at the right pace. I don't even know. No, are you taking me calculus based, right? Yeah. Okay, so this is how it works.
You know, your skin may
Algebra
get a
based
little
people,
irritated,
they stay
you're
caught
just
up.
getting used to
The
it before
calculus based version of caught up is like, oh, I guess I'm ahead. Well, that's what it seems to be, because everyone I know that has calculus based is like about the same. That's where I am, where I just need to do the first Shut up.
Yeah, that's usually.
Answers.
Yeah,
You have all the answers. Yeah. I don't want to hear
I
shit.
don't use that. You still have to like know
Oh,
how
yeah,
to
no,
do
I-
yourself to know how to do it.
Yeah, definitely. I'm trying to like.
That is a saving grace though.
Using it as
That
much as I can.
you probably full saving grace that you
Yeah,
All right, looks like we have a few people online, and then welcome everyone in class. And so I wanted to talk about some announcements before we get started. So did you guys get email from like ASG that they want to have this student forum about like a student activity fee? It came up pretty quickly. They have it scheduled for next Tuesday at 11 a.m. on the Riverside campus. So right now it's happening on the Redwood campus, so super short notice on that one. But next week it'll be on the Riverside campus. Unfortunately, it's during our entire class time, but I think it's like kind of important, so I was kind of feeling y'all out. Because kind of the idea with the student activity fee is to give the ASG more power and kind of more autonomy, and like, you know, that's kind of benefits y'all. And they are providing pizza as well, so I was kind of thinking, like, should we start lecture late on the 13th? And next week will be exam week, though, so Tuesday will be a review. So that's my plan for Tuesday. So what are y'all's thoughts?
Do we get a say in if they get more funding or not? Like, can we all band together and be like, no, don't take our money?
Well, I guess it depends like what outcome you want, because the problem right now is ASG's budget is controlled by the college, and I guess at other community colleges and universities, they collect a fee separately, and then that's also, you know, up for debate, like, well, how much should the fee be? What's that gonna, you know, cover? So, yeah, all that's up for debate. I think it's a good idea in some ways to have a fee, but that's just me interjecting my own thoughts. But that's why you should go and like talk to ASG. And Alira, I don't know if you want to jump in because you're on like ASG, so you.
A little bit of a general idea. The main point of the student initiative fee forum that we're hosting is to just get a general feel on how students feel about the fee. If they like it, you know, some of our plans on what we could do, like, you know, paying for possibly parking passes on the Riverside campus for students, scholarships. We're trying to bring back the, what is it, the five, sorry, what is it, I keep running up there this week, the Phi Theta Kappa National Honor Society back to RCC, and we were thinking of maybe if we were able to bring it back when students were needing the financial assistance for the membership fee, where we would go provide back to students as well, working with you to get that done. It's just a general feel and how students will feel about the fee and what they'd like to see the fee used for if they'd like to see it.
So. So does that mean we should delay lecture then next week to 11:30, and maybe y'all like rush in and like, hey, we're here from Chem 222, we need our pizza and our opinions heard before we go to lecture type of thing? Because I mean, I also want you to get food too, but yeah, I mean, it's a really important issue, especially with governance, and I think it's really important that you get involved in, you know, your local government down to your community college and how your student government runs, like all that is super important. And I know it came up really fast in like the chat, like everybody sounds pretty clueless on this, but that's why I think it's kind of important that we go. All right, so do people want to do that then? If you strongly protest, you can also speak out. And if you don't want to go, I can still be here and just like, you know, answer questions with you for 30 minutes while other people attend that, so. All right, let's make that official then. And I'll see if I can get some flyers or something that says like more about what's going to be the discussion, because I think people in the chat are kind of asking what the topic was going to be. But yeah, it'll be about like just what the fees would be used for, and I'm not sure if the chat could hear you, Alira, but. So let's do, so next Tuesday is the forum with ASG. And so it's from 11 a.m. to 1 p.m. And so we will delay lecture. And I'll probably send an email to Chelsea Doherty. She's like the club advisor she's a faculty club advisor. And so I'll let her know that y'all are coming and, like I said, need your opinions heard kind of first so you can get back to class. And so Tuesday, though, will be review. And again, you can come ask questions. If you don't want to participate in ASG from 11 to 11:30, I'll hang out here as well. All right, does that sound like a good plan? I'll try to get more information if I can earlier, if you have any flyers about just what's going on, so I could post. Are there any other announcements, questions, comments?
I do have a question, mainly because I'm kind of new here. So with the exam, do we have like a, say, either like a study guide or something with it, or?
I usually don't post like too much of a study guide. I'll see what kind of a loose study guide I have, and I'll try to post it since it is next week, so I'll look at that. But generally what I do is on Tuesday, I do like a review that's very similar to the exam. And so it has like the same type of questions, just maybe, different numbers, different molecules. So that way on Tuesday, you have a pretty good feel of what's going to be on the exam. Yeah, show up Tuesdays generally, and then Thursday we'll take the midterm.
Is it open note like last time?
Yep, so same thing, all my exams will continue to be open note. Again, just don't Google the exact question, but I usually make them tricky enough that that's hard to do. But yeah, same policies will apply. And then make sure you get the paper, kind of your topic idea turned in. I haven't seen a lot of those turned in, but I think people are still stewing on them, so ask me for help. Again, if you need papers, I can send them to you, or at least try to get them past the paywalls. I can't always get everything, but usually I can get around a lot of them. Other announcements, questions? And so again, our midterm is next week. That will be facing us. And it'll be similar format, a few multiple choice questions, and then a free response like we've been doing. All right, so let's dive into the chapter then, unless there's any other things we need to talk about. And so let's look at this example and how this little wood frog survives. And so unlike most cold-blooded animals, the wood frog has the ability to survive very cold temperatures by hibernating. And so it's in a partially frozen state, no heartbeat, no blood circulation, no brain activity. And then its vital functions, though, can be revived within 1 to 2 hours of thawing. And so the question is, well, how does a wood frog do it? And so what's the problem when you freeze things?
They expand.
So they expand, right? Well, they get cold and then they expand. And so the problem, right, water, we mentioned, of course, it expands. And when that water expands, right, it destroys those cells as well. So it bursts all the cells. And, right, same thing it does to your meat. So you don't want to, or your veggies, right? So you see your poor veggie cells, all of your cell walls get destroyed. And so how does a wood frog do it? And so the wood frog can survive, though, because it can flood their blood with sugar. So it injects a large amount of glucose prior to hibernation. And so this high concentration of glucose then prevents the blood from freezing, since that concentrated solution then lowers the freezing point. And so we'll be talking about this concept, right, freezing point depression and later boiling point elevation. And so this is giving you a taste at how this freezing point is lowered, so we can look at the molecular level and we have our little water molecules, but then disrupting them from forming, right, the ice patterns is our sugar here. So now it's disrupting those intermolecular forces, so you have to lower the temperature to get it to freeze. And so a little bit of a recap of just what is a solution, so we're all on the same page. So solutions are defined as any homogeneous mixture, so just uniform throughout. And it's made up of 2 or more chemical substances. And we've mainly talked about aqueous solutions, and that's what we've seen in lab. So, right, any of our, like, copper chloride, for instance, all of those, right, the stockroom dissolves in, like, an aqueous solution. And, of course, we can also have organics, but we haven't talked about organic solutions too much. So we'll just put that organics, so any organic solvent, alcohols, ethers, etc. And then, of course, right, whatever substance is dissolved in our solvent. And so solution can also be composed of different phases. So generally in this chapter, we'll be talking about, right, dissolving a solid in a liquid, but we can also have a gas in a liquid or a gas in another gas component. And so 2 vocabulary terms that we've mentioned, but we'll highlight again. So again, we have our solute, so the thing that's being dissolved, so usually a solid, but not necessarily. And then your solvent, and so this is usually the major component. Again, could be some exceptions, but just usually. And the solute is always the component being dissolved, and AKA mixed into the solvent. And so like I mentioned, right, the major component is usually the solvent, and the minor is usually the solute. And so we've kind of been touching on this, so we'll keep discussing this and looking at things again in more detail, right? So we've looked at kind of the polarity. And so we can think back to last chapter. So last chapter, we basically divided molecules by what kind of intermolecular forces they had. So we had our weakest, right, our London dispersion. So that would be for our nonpolar molecules, right? Then we had our dipole-dipole, which again was just polar molecules. And then, of course, right, our extreme hydrogen bonding. And so now when we say this, that like dissolves like, well, now we're looking at these intermolecular forces, right? And we're talking about those interactions. And we had already kind of stated first quarter, so we mentioned, right, we're trying to look at those solute-solvent interactions, and, right, are those solvent-solute interactions stronger than with itself, right, with the solute-solute? So, right, thinking of sodium chloride, right, is the attraction of sodium chloride stronger, or is it more attracted to the solvent? And so with that, we're thinking of all these intermolecular forces. And so that's where we get this like dissolves like saying, or polar with polar, and nonpolar with nonpolar. And again, right, think back to how the soap works, how you had to have your long chain of hydrocarbons to mix with your fatty, greasy parts, right, your nonpolar parts, so that dissolved, and then how it was able to form the micelle with that polar charged part that, of course, right, hydrogen bond. So we're just looking at everything kind of, again, in more detail. And then, of course, we've already seen that nature has a tendency towards mixing, and again, just recall, maybe we have to do this experiment since we haven't done it, but you guys have all seen, again, a drop of food coloring, right, mixes to the whole container. So it just has a tendency to, right, for spontaneous mixing, and so that's, again, what we're seeing, right? Chaos is always more energetically favorable. Right, just let me know if I'm going too fast or slow. And I feel like we've kind of had to talk about some concentrations in this class, right? We've already touched on molarity. So now we'll just kind of go through different concentrations and again, just kind of redefine some of these things. And we've seen this, right? Solutions have different compositions. So we've seen in lab 0.01 molar acid, we've seen 3 molar acid, 6 molar acid, right? It all depends on the application. And so we have these kind of vague terms of dilute and concentrated, so those can just kind of describe a solution. So in general, I would say dilute is less than 3 molar, but again, this is just a very vague term. And that's why we have, right, all these different units, so we can really accurately describe what is our concentration. And then concentrated, I would say, is anything over 6 molar. And usually, right, there's additional safety concerns with using stronger acids. Obviously, there's immediate burn concerns. And then, of course, if you're working in larger amounts, that's, extreme hazards. So you have to, again, consider all those safety issues. And it's like we mentioned, what we care about is the concentration. And so we'll, again, look at least a lot of the major units. And so all of this is to say we're trying to describe, right, the amount of solutes, or how much did we dissolve in a given amount. So this is what I call our quick kind of cheat sheet with all our different units. So these are all the ones we're going to be discussing, and then we'll look at them all in detail. So of course, we've seen molarity, then we'll look at molality. We've touched on mole fraction, right, with our gases, so that should feel similar. But again, we'll go all these more slowly. So let's just start with molarity. So we should feel pretty good about this one. So again, just for completion's sake, it's defined as a mole per liter, so mole per volume. And so if we're looking at a sugar solution that is 2 molar, then we're saying that 1 liter of solution contains 2 moles of sugar. Or of course, right, we've learned how we can scale that up and down. So 2 liters would then have 4 moles of sugar, and half a liter, 1 molar. And again, we've seen this equation. Let's highlight it. And so now let's compare that to molality. And of course, right, they're only different by this one little L, and then symbol of small, so lowercase m. So we don't often see a lot of molality, but I think other places use molality. So some people argue that molality is more accurate. And so if we look at molality, now it's going to be moles per kilogram. And so it's considered more accurate since we're going by mass. So volume can change slightly with regards to temperature. And so again, this is the advantage. So in a different field, you might see molality. And so again, just write down the definition. So molality is then moles of solute over kilograms of solvent. So notice it's just the solvent there. And so now we have this kind of vague parts, solute and parts. And so this is because, right, it kind of depends on what the measurement is. And you have to look and see what you're given. So basically, right, your parts could be in any unit. So it could be the same unit. So sometimes you see mass, so grams per gram. So some sort of percent mass by volume gram. could be, of course, in kilograms, could be in pounds. And then again, we can see, right, mass per volume, so grams per milliliter, grams per liter, right, kilograms per liter. So anything, there's basically, right, endless possibilities. So you have to look at what it's saying, if it's like a weight by weight or weight per volume. So you always have to watch out for that one. And so our percentage, so again, percentage, you have to look at if it's, again, mass by mass or mass per volume. And of course, if it's percentage, then it means parts in every 100 parts. That makes sense for our percentage. And so in this example, it's 0.9% by mass. Okay, so then that's telling us there's 0.9 grams of solute in every 100 grams of solution. And again, right, that's grams of solute then per grams of solution. And so now let's look at parts per million. So parts per million, of course, that would be 1 in every 1 times 10 to the 6, right? So that's our million. And so this is sometimes difficult for me personally to translate, especially if you're reading a problem. And so I like defining it as this. So instead, you can say how many milligrams of solute are in every 1 kilogram of solution. And so we can see, right, we still have our factor of 10 to the 6. So milligrams is 10 to the negative third, right? Kilograms, 10 to the third. So if we divide those, that's still 10 to the 9th difference. So this is my preferred method when trying to figure out how many parts per million you have in your solution. And so again, it depends on your problem. And so we can set up, right, our parts per million, again, amount of solute and amount per solution, or milligrams per kilogram. So I like that. And right, we usually see parts per million if we're looking at like a water quality report. So you could pull up like the Medford water quality and look at all the fun things that are in there. And so the next common one you'll see is parts per billion. So this is going to be for more nasty things. So I'm sure they measure like arsenic in parts per billion and lead. So things you would not want a large amount. And so of course billion is 1 times 10 to the 9th. So right, how many particles in 1 times 10 to the 9th particles of solution? Or, so again, I prefer this method. It kind of helps me convert back and forth. So so however many micrograms of solute over kilograms of solution. And so again, we can derive, right, our 10 to the 9th factor. So micro is 10 to the negative 6, right? Kilogram, 10 to the 3rd. And so, of course, right, we can divide and see that 10 to the 9th. That helps. Questions on these so far? So let's look at mole fraction. And so maybe we should also go over your quiz, because a lot of people had an issue with the last problem of your quiz, but it was basically just a mole fraction problem. But a lot of people made a lot of little mistakes, so we might redo that. So let's look at what a mole fraction is again. And so we said, right, the mole fraction is a fraction of the moles of one component and the total moles of all the components, right? And so it doesn't matter how many components you have, you just add them all up. And so let me. So let's actually switch to your quiz and figure out what happened. And so we need the mole fraction. So let's try this out. Let's do, so from our quiz, we had 10.8 grams of xenon and 25.3 grams of sulfur hexafluoride. Exert a total pressure of 2.31 atm, and it asks for the partial pressures. And so, to find the partial pressures, we basically just needed the mole fractions. But a lot of things went wrong. So try to redo this right now. I'm going to go ahead and pass out the quiz while we take a few minutes to look at this and figure out what happened. Because even if people had the right idea, there are still a lot of calculator errors that happened. So let me. There were a lot of algebra errors, that's why I'm very dear. So if you're in the chat, you can type out your thinking or any answers you got along the way. I'll give people another minute or two in class to kind of, yeah. Yeah, so you might have already gotten it right on the quiz. Maybe you can think back of what we did. So start walking me through, and I see it in the chat. So somebody asked, do we convert to moles first? And so yes, so right, that's the first step, is we have to find moles of each. And that's where things went. Some people had a few algebra errors there or something. And so let's just divide that. So we need to find, right, what's 10.8 moles, or sorry, grams of xenon. So how many moles is that? So what's the molecular weight of xenon? 131.293. And again, that's where showing your work is always advantageous. There are a lot of, like I said, a lot of calculator errors along the way. So then we should have gotten 0.082, and we could round it to 2.3 for now. And then, right, repeat the same for our sulfur hexafluoride. So we had 23.5 grams. And then what's the molecular weight of sulfur hexafluoride? So other people get, so 146. And I saw some weird numbers for this, so I'm not sure what happened. And again, help me so double check my numbers. So 0.173. And again, that's where things kind of went squirrely. And so what happens once we find the moles of each? And what was our mole fraction definition?
First thing I do is write out like the mole fraction formula. It's like, I just put like N xenon or N sulfur hexafluoride divided by N capital T for total moles.
So that works.
So I add those two together first to get the total moles.
And so what's our total moles?
About 0.255.
So 0.255 you said? And you could round it, so yeah, so 0.25. 5.6 or so. Try not to round too much. Or, sorry, let me fix that. 0.256, so something like that. And so again, I saw funny numbers there, but showing this sort of work was good. And so then, right, then we just had to find our mole fraction. So right, this was just our definition of the mole fraction. And so now we can find it for each one. So with xenon, 0.0823 divided by the total moles. You could have written them just added together in your work. And then so that gives us our mole fraction, which for our purposes, right, we want to multiply by the 2.31 to figure out what percentage of the total pressure it was. So 0.0823 divided by 0.256. And I think some people like wrote this number down as their answer as well, so there are all sorts of crazy things that could happen. So then you got 0.743 for our pressure. So that was for xenon, and then just repeat that. Or you could subtract right at this point if you didn't want to do the mole fraction. Or that was another way to check your answer, was add the two partial pressures and see if it added up correctly. plan, so then getting like 1.56 or so ATM, or 5.7, you can tell me with the rounding. So do we feel okay on the quiz now in mole fractions and what to do with mole fractions? Is that a real question, or? I guess,
Like, I understand the process and everything, but like, what is the reason that we should, like, like using the equations that we got, like the P equals like, PV equals to nRT, right? And then that's how we would assume that the volume and temperature and R are all related. Why is that? Is because they're all constant, and we only need the pressure?
well, that's part of it, but right, it's also just kind of the definition and what we're given here, because we're only given, right, the total pressure, and then we're given the gram mixtures, right, but then we have to go back to Dalton's partial pressure law and just know that it's based upon the N, so the moles, right, and we know the moles are additive, right, because the identity of the gas doesn't matter, so it's like we have to figure out, well, how many moles are there total, right, and that's contributing to the pressure of 2.31 ATM, and then we're just finding the mole fraction to then figure out, well, how much of that is xenon versus the sulfur hexafluoride. Because that's all our mole fraction is telling us, right? It's just like, it's a composition. So if we go back to here, right, it's just telling us, right, our mole components. So it's just a percentage by moles, essentially. And then it works for our pressure problem, right, because that's related to Dalton's partial pressure and PV equals nRT, so we went over how that's additive. And now here, right, we're just using it again and just saying, hey, this is how we're defining it by, you know, fraction of moles over total of moles. I don't know if that helped any, but. All right, so let's work on some practice. I guess let's finish up our mole fraction. So like we saw in our practice, right, it has no units. It's just giving us kind of our ratio and just our percentage of moles. All right, so let's do some practice. So we just learned all those different things. And so now let's figure out how to report them in all these different units. So we have a solution of 17.2 grams of ethylene glycol dissolved in 0.5 kilograms of water. And the final volume of the solution is 515 milliliters. So take a few minutes, figure out molarity, molality, percent by mass, mole fraction, and mole percent. everyone's like super focused, but we'll at least start going over them. So how do we solve for molarity?
You find moles both ethylene glycol first.
So moles of ethylene glycol. So then we have to find molecular weight.
Yeah, I got about 62.068
Is that roughly what other people got? That sounds right. Excellent. Classroom agrees. So then you can figure out moles. So 17.2 divided by 62.068. So did we all get 0.277 moles? Excellent. And so what do we do with this moles information? So divide by my volume. And then you said convert to liters, so that sounds excellent as well. So 0.515 liters. Oh, sorry for the bad 5. 0.515. And so then did we all get like 0.538 molarity or so? Excellent. And so again, that's big M for molarity. And so now molality. So what's molality? What information can we use? So moles over, you said kilograms of solvent. So what do we need to plug in for this one? So 0.277 moles again. And then what do we divide it by, you said? So excellent. So just by the mass of water. So 0.277 divided by 0.5. And then we should have gotten something 0.554 molality.
So for molality, you divide by I think it was kilograms of the solute, not the entire solution.
Yeah, it's just the solvent.
Not solute. Yep.
Yeah, correct. Yeah, whereas,
But for molarity, you take the entire of the solution.
yeah, so that's where the small discrepancy is, right? Since when we make our, like, let's just say, right, we're making our 1 molar solution, we have our liter flask, we're not accounting for any space that the solute occupies, right? If it's a solution or a solid thing, right, it still occupied something. But yeah, we don't account for that. And so you can at least appreciate, right, the small difference in molality versus molarity.
I got on my calculator, 0.554.
Oh, did I type? Oh, you're right. Sorry, I just didn't translate it. Thank you. And so again, that's why the argument is molality is better, but at least with the type of work that I do, I never use molality. Again, it's field dependent, I'm sure.
It's better than why does it have a lowercase then?
Things I don't know. So what do we do for percent by mass? Oops. Percent by mass. So you said we take the mass of our solute, so that was 17.2 grams, and then divide it by the whole. So this is percent by mass. So percent over whole, so then 500 converting to grams plus 17.2. And so let me punch this in. And then, so we want to report this as a percent, so I'll multiply by 100 So then 3.3%, I think you're saying? So 3.32%. No, it's okay, because it's just like this, what the solute is, yeah. Although it wouldn't be wrong, it just may not be that descriptive though either, since you want to focus on what you're dissolving. All right, what was D? So D was mole fraction. And so 500 divided by 18, so how many moles of water did you get? Yeah, even if I round it, I still get like 27.8. We can round. So 27.8 moles roughly of water. And so right from before, we had said we had 0.277 moles, right, of ethylene glycol. And so now we can set up our mole fraction. So 0.277 divided by our total moles of stuff. So something like this. And then double check my math when I finally punch it in. And so we can convert this to a percent as well. So about 0.99% or so for our mole fraction. Questions about mole fraction or anything? And so what was E again? So mole percent, oh, I did it. My bad. So I guess mole fraction, I should have technically just left it as 0.0098. I got too excited.
0.99% is a bit more helpful than 0.277 over 0.277
Yeah.
plus 27.8.
All right, so that's our mole fraction.
That extra step.
All right, so we're feeling okay about these. Just how to do them. Excellent. Should we take a little break before we continue on? All right, let's take let's take a little break. So what, like 5-10 minutes?
15.
All right, we'll do 10 minutes. You guys are. Oh, I accidentally did them really quickly. I didn't realize mole fraction and mole percent. So it's just multiplying by 100. All right, yeah, we'll take a little 10-minute break. Try to be back at 12:05-ish. And then if you're in the chat, you can also use the break time to ask me questions. Again, you can email me if you're too shy to chat. I'm a little concerned because you're not the only person who said that you're having trouble with the previous chapters. So I'm just trying to figure out what the questions are. So that goes for y'all in here too. I'm hearing there's like chapter 13 issues, but I don't know what the issues are. Oh,
I
but
don't know if it was in the grade book.
let me double check that. Because it should have, but sometimes I skip them.
I can show you the paper too if you need me to.
Oh, I believe you. See, where is your homework?
Oh, yeah.
Chapter 9. Yeah.
Thank you.
Well, thanks for letting me know. What the heck?
I think we just like kind of set it up. I don't know if we actually determined.
She's starting the class,
I think this is like last term's thing, plus next
Oh,
year's
I
thing.
do have a question. So the chapter 16 reading results say they're due yesterday. But it says they're like separate, like in writing, but the.
Oh, yeah,
on
that's.
Blackboard it says the.
Well, I'll fix that.
So they're actually due the 7th.
Or they would be
Well, I
due
guess
like
it'd be
next
that
week.
Sunday.
Yeah, it should be due like next Tuesday. I think I have the dates all wrong everywhere.
You had blue liquid at that point.
The writing is like, I'm choosing fuels, hydroelectrolyzers, biotech.
Yeah, just as long as there's like good. So hydroelectrolyzers? What are you talking about? What's that about?
It's about splitting water into hydrogen and oxygen.
Oh yeah, yeah. That's a pretty hot topic. So that would be cool.
So I can do that.
Yeah, yeah. I would start looking at the literature because there's like a lot of literature on that, so you want to narrow down exactly.
Suggested that since he kind of works with materials, he's also talking about hydroelectrolyzers.
Yeah, because that's the only thing you want to focus on is like what do you want to talk about. So maybe if you know something about materials, then you could focus on like where the material research is at, because that's going to be like a heterogeneous catalyst as well. So that's like more useful for industry, arguably. So yeah, you just have to see where the research stands.
Well, right now, I'm thinking about the hydroelectrolyzers. I've been doing fuels for a while, so I know a little bit about fuels. When choosing the topic, I had a hard time choosing between fuels and explosives. But I didn't want to be on the FBI watch list. I chose fuels.
Yeah, and you can also give like a broad overview too of like energy density too, and then yeah, it just depends how you want to structure it. But that's like also a good thing to talk about when we're talking about fuels.
Thanks for answering my question.
Yeah, and just you can always email me more papers or whatever as you find stuff.
It's like 5:30. Some members.
My paper. So I was gonna do it on like the biochemistry of the Krebs cycle.
Oh,
Is
nice.
that?
Yeah.
Okay. So I guess that's what I'm gonna do.
Sweet. Yeah, and then you can give us a detailed look.
I chose it because I've studied it twice, so hopefully
Yeah.
it'll make a little more sense to like
Yeah.
see it versus something I've never studied before. So
Yeah, exactly. And it's you can always think of like what like, I would say lens you want to put to it, because you can also go into like a little bit of the energetics of it if you can find information, or just like, you know, a broad overview of how it works. Because even just talking about each step mechanistically is like super useful too.
And it's pretty small market, like, the chemicals that are in it are actually like inconsequential.
Yeah. Yeah, and like showing that mechanism, like that would be really cool in detail.
And when we're turning in, are we turning in like our topic ideas and our articles or an outline?
Either or. So I really only require like the topic and articles. I just suggest an outline just to kind of help you. So I can kind of see, because the thing with the outline is like if you outline it, you might see like, oh crap, like maybe my papers aren't as good. But yeah.
If I put in 2 papers and then end up not using them in my.
Yeah, it's not a big deal. Yeah, we're just trying to like make progress and learn, because yeah, as you read more, you might switch.
That's the most thing I've heard is that kind of that's like we don't even really understand what it means. Like there's not a lot of if it exists, it's not on our yeah, but like we're kind of on a one track road.
All right, did we all make it back? We didn't lose anybody? All right, so now let's go back to our lecture. And so basically what this chapter is also talking about is, in general, this thing called colligative properties. And so this colligative properties, it refers to any properties where the value depends on the number of solute particles. And so we'll look at, again, what this means as we continue in this chapter. And this is also alluding to, right, our boiling point, our freezing point. And so why this occurs is the difference in the value of the property between the solution and the pure substance is, of course, related to those differing attractive forces. And again, those solute particles occupying the solvent molecule's position. So, right, that leads to a lot of disruptions in those intermolecular forces. And so then we'll look at this Van Hoff factor. And so I feel like it kind of overcomplicates this, so what this means. And so what we're saying, and let's just start with like sugar, for example. So sugar, we said, well, that's a molecule, right? So it does not disassociate. So when you have let's just say a 1 molar solution of sugar in water, right, you still have 1 molar of sugar. But now we're saying, well, let's look at these ionic compounds. So let's just start with sodium chloride for comparison. So let's just say, right, we have a 1 molar solution of sodium chloride, right, so meaning we had 1 mole of sodium chloride. However, when it disassociates, right, you're really getting a sodium and a chloride, which means you have 1 mole of sodium and 1 mole of chloride, which is effectively a 2 molar ion solution. And so for our purposes, we'll just be looking or going by kind of our expected factors, so we expect everything to fully disassociate. And then this is just telling you that our measured Van Hoff factors are generally less than what we would expect, so we'll look at kind of the chart and compare. And so our measured Van Hoff factors, again, might cause our change in temperature to be lower than expected. And so again, right, this I is just saying how many particles dissolve. And so it makes more sense if we look at the examples. So right, we did sodium chloride. So we said, and this is just comparing essentially like 1 molar solutions and just looking at our Van Hoff factor. And so we can repeat this, and so right, we can see the oddities. So magnesium sulfate, we expect it to fully disassociate and effectively be, right, a 2 molar solution. So 2 molar of ions. But then what this is saying, right, is in actuality, it's a little lower than expected, so our measured value, and again, for our purposes, we just need to know our expected one. So at least just appreciate it that, right, again, there'll be, not everything is perfect in the real world, basically. And so looking at magnesium chloride, so let's just kind of go through these examples. So again, magnesium chloride, if we say we have a 1 molar solution, we make 1 mole of magnesium ions and then 2 equivalents of chloride. So that gives us effectively 3 molar of ions. And so you see that right with our Van Hoff factor. And then potassium sulfate. So again, same thing. We expect it to have a Van Hoff factor of 3. So it disassociates to 2 potassiums and then 1 sulfate, so our polyatomic. Again, it has a lower one, but not that relevant for us. And then, so now looking right, we could have iron chloride, or iron 3 chloride, we should say. I don't know why I wrote it like that. And so again, right, if we have 1 molar of iron chloride, it effectively becomes a 4 molar solution. All right, so that's our Van Hoff factor. And actually, while we're at it, let's look at the homework. Let's see if I can pull up the homework. All right, so here's our homework. And so let's skip down to kind of this 6, 7, 8, 9. And so all this is dealing with the Van Hoff factor. And so we probably won't go through all of these right now, But what you want to do is effectively, right, write their true molarity. So take a second to do that, and then we'll go over it. Right, look at these, which one disassociates, and then what is their effective molarity, right? How many ions are there in solution? If you're still with us in the chat, you can also write down your answers.
Wait, but the values that you gave us, are those the band off ones, or are those like the normal ones?
Yeah, so these are the normal ones. So you basically, what I'm asking you is like figure out your Van Hoff factor and then your effective molarity, essentially. So then looking at our sucrose here, so what's the Van Hoff factor for sucrose? Yeah, so 1. So you can show your finger as well, right? So it's just 1, which means, right, our effective molarity is still 0.1 molar, so that hasn't changed. What about for sodium chloride? So what's its Van Hoff? I see some fingers. Yeah, so 2 is a consensus. Do you have a question? So just because we know it's a molecule, so it's sugar, so we know, right, it's a discrete molecule. So if this had been like aspirin 2, right, THC, limonene, so any discrete molecule is still the same. Yeah. Yeah, so anything that disassociates, right? So generally it's our ionic compounds. And then for our purposes, we won't get into acids with this Van Hoff factor, because that would be weird, right? The weak acids. So strong acids do disassociate, if we were to see that. So what's the Van Hoff? Oh, everybody said 2, right? So sodium chloride is 2 for a Van Hoff. So what's our effective molarity? So 0.16 molarity. And then this last one, so what's the Van Hoff factor? So I see fingers for 3. So right, 3 is our Van Hoff. And then so what's our molarity? So 0.09. All right, so that at least kind of pushes you in the right direction. So now we'll have to go back and talk about, so these are all the colligative properties, right? Our vapor pressure, our boiling point, but we'll continue in the chapter talking about that. I just wanted to point this out because most people sometimes start off on the wrong foot of just not even having the correct effective molarities to compare. All right, so we finished that up. So do we feel okay, right, about these Van Hoffs and their kind of expected molarities? So, right, we're just multiplying how many ions it disassociates into by its molarity. And so now the question is to get into all those colligative properties and figure out, well, how does the presence of dissolved particles affect all these different things? And so now let's look at our vapor pressure. And so the key point, so the vapor pressure of a solvent above a solution is lower than the vapor pressure of the pure solvent. So, right, that's the key point. So, right, our solution is lower than the vapor pressure of the pure solvent. And so that happens since our solute particles replace some of those solvent molecules. And so this affects, right, our equilibrium. And so now I forgot what chapters those are all in. So we could go back and look at our liquid vapor equilibrium curves if we need to. I think there are charts later. And so if we add a non-volatile solute, of course, this can reduce the rate of vaporization. We could also, of course, have the reverse effect, but again, most of the time we're talking about dissolving solid particles, and so that would reduce our rate of vaporization.
Okay, so this is only for adding like something basic like a salt or something. Like if you added something that had a higher vapor pressure than this solvent, then obviously the vapor pressure overall would increase.
Yeah, and so we'll look at other perturbations kind of later in the chapter. We'll kind of see like, oh, is the vapor pressure higher, lower, and then what does that say? But yeah, right now we're just kind of talking about dissolving our salts, so kind of thinking more simply, right? So this would, a good analogy is like the argument of should you add salt to your pasta water before or after? And then, right, people go into the science that it takes more energy to get it to boil. And then, I don't know, the cooking experts can tell me whether you want a hotter temperature or not for the pasta, because then there's some debate over that it could overcook it. But it seems all trivial, but I don't know if it actually matters. But so now we have more debate. And I've heard different things on that, too. I think we need a cooking class of chemistry. That'd be fun.
Right away, and usually you don't need to add oil, but to make it easier, yeah. That's fair, that's true.
Yeah, anyways, we'll get into our debate later. But right then, our equilibrium is, of course, reestablished. And again, it's a smaller number of vapor molecules. So again, our vapor pressure is lower. So the other kind of cool phenomenon is a concentrated solution will draw solvent molecules towards it because of the natural drive for materials to mix. And so a concentrated solution will draw pure solvent vapor into it. And again, that will result in a reduction in vapor pressure. And so we got some pictures. So again, vapor pressure lowering. So for the most part, again, if we're dissolving sugar or salt or other ionic compounds. So now we can say that our vapor pressure is proportional to the amount of solvent. And so our effect is vapor pressure lowering, and so our difference in our pressure, so of course this is our pressure of our pure solvent minus our solution, and that's given by the mole fraction. So notice, right, that's our mole fraction. So whatever our solute mole fraction is times our pressure, so times the vapor pressure of the pure solvent. Oh, sorry.
Yeah, I just needed a formula.
Sorry.
The little dot that's after the P, with the P solvent, does that mean like pure? Yeah, that.
It's just like the pressure, yeah, the pure, so like known factor, like known amount. Yeah, so then it gives you the difference, which is usually lower, at least for our purposes. And let me know if I need to go back to the formula. But then this is a picture that kind of was going with all the words that they were trying to say. So, right, they said, okay, we have, let's look at this, right? We have a closed system, so we're looking at two closed systems, right? And then in our system, we have a beaker of pure solvent, and then the other one of some sort of concentrated solution. And then it was saying that our concentrated solution has a tendency towards mixing, and so it's going to want to mix, so this pure solvent level would drop, and then the level of this solution would rise. So that's kind of interesting.
Because the molecules are kind of like drawn to the solution.
Yeah, and like they're drawn towards mixing, so it's kind of strange, but yeah, it's like the solution wants more of the solvents to like dissolve.
It's like losing concentration for you, right?
Yeah, so similar effect.
Through the air rather than typical, just through like a membrane.
Yeah, exactly.
How long does this process take?
It would probably take like a while, right? And it would depend on the vapor pressure. So something like ether would move faster than something like water. So, but yeah, I would say at least like 24 hours or something to notice it.
When you say notice, does like drop by like a centimeter or like?
Well, that would depend on the solvent, but and like the concentration, because right, depending on how concentrated, it's going to want to draw more in or less in. But yeah, I would say like a centimeter or so. Again, it depends. You have to look on YouTube. Maybe someone's done the experiment. And so like we said, so this is related to, again, our Raoult's law and vapor pressure. So again, right, we just said that our pressure of solvent in our solution is equal to our mole fraction, of our solvent times our pure solvent. So similar formulas. So either you can use this to find your pressure, or again, find that difference if you're using the solute. So this is the solvent formula. And of course, since your mole fraction is by definition less than 1, then your vapor pressure of the solvent in solution is always less than your vapor pressure of your pure solvent. So let's try a practice problem. So calculate the vapor pressure of a 25-degree solution of water containing 99.5 grams of sugar and 300 milliliters of water, and it tells you the vapor pressure of pure water is 23.8 torr. how are the calculations going? What are we doing? So some of you are busy plucking away. So what are we calculating and how do we get there? So mole fractions, we need mole fraction, and this time we can do it of the solvent, right? And then we'll just multiply it directly. And so now let's get some moles of things. And so our solvent is water, and so we could find moles of water. And so they gave us the density, so 300 grams divided by 18 roughly. So we get about 16.65 or so moles of water. And then what do we get for the molecular weight of sugar? So this is C12H22O11. So that sounds good. So what other people got, or at least roughly? Okay, I see some nods. So then we gotta find moles of sugar. So 99.5 grams divided by that 342. So I get about 0.291 moles of sugar, and I see people nodding. So then we set up our definition for mole fraction. So for our solvent in this case, so 16.65 moles of water over the total. And again, your answers could vary a little bit with rounding. And so I get like 0.98 for the mole fraction. Is that what other people got? Just check in. So 0.98 for a mole fraction. And so then we can find our pressure then of our solvent in solution. So multiplying it by our normal vapor pressure. So times our 23.8. And so I get a new vapor pressure of 23.4 or so. And then, right, you can always just give yourself a quick sanity check. So it's a little bit lower, so that makes sense, right, for our solution. And not a crazy amount of sugar, so don't expect it to make too much of a difference. So that looks good there. Questions on this problem or mole fraction or anything, or vapor pressure? All right, so let's look at our next colligative properties. And so with this vapor pressure lowering, so now this leads to different effects. And so the effect of that is, of course, right, with our vapor pressure being lowered, then the temperature required to boil the solution is then higher than the boiling point of the pure solvent. So now this is back to our pasta argument. And then, so now we also see that this results in the temperature required to freeze the solution being lower than the freezing point of the pure solvent. So freezing point depression. And of course, there hasn't been too much of it this year, but that's why they either salt the roads or sand them. So what's the big problem with salting the roads? And Oregon does a good job with this, so that's why they use the rock. So why is that? Yeah. The, that's okay, but the big one, yeah, is a water system. So Oregon's pretty good about protecting the water system. And right, we have all these nice rivers, but then what happens if you just put a bunch of, salt over time? If everyone's icing all the roads, all that runs off into the rivers, so that of course messes things up. But yeah, so yeah, exactly. So we got to protect the fresh water. So that's really important. So I think here they use that red rock or something. I see a bunch of that. But that's a lot better for the environment. Not to mention that the salt can also destroy the undercarriage of cars. I haven't lived out east, but I've heard horror stories that you gotta wash your car in the winter, or else your whole undercarriage rusts off. Yeah. So. Oh, really? Okay. So yeah, anywhere there's.
Year round with their salt and
so that doesn't help. So.
don't drive far from here.
Good to know. All right. So now let's look at this graph. So this kind of helps. And so now we're looking at our triple point graph here, right, with our phase diagram. So solid, liquid, gas, just like we did before. But now we're looking at the difference. So we have our pure solvent in blue. And so now look at this line, how it decreases. So this is our melting point. And so now that's lowered. So right, freezing point depression. And then comparing, again, our pure solvent, now we have our liquid gas, so our evaporation. And so again, now we need more energy. So you can see this is our vapor pressure curve, right, where it crosses the 1 ATM, and then notice how it's higher here. So now, right, that's why we have to have our higher boiling point. Yeah. It would depend on those solute-solvent interactions, so maybe if you put something more volatile in there. But that's just not the usual effects. You would have to add another more volatile substance. That just doesn't make sense to me. Just energetically.
I heard someone say that to me, and I was like, if it's closer to the higher temperature, then it takes less energy than to get it from the lower temperature to the higher.
Yeah, I'm curious what started that, though. All right, so then we have too much tangent. So we have our equation here. And so for our purposes, we can quantify our change in temperature. And so again, right, if we're talking about freezing point, it's going to be lower. So this is normal, lowered from our normal freezing point. And so this would be likely dependent on what values you were given. And so usually what is given is this molality times our proportionality constant. And so this is just another constant that we have to look up. And again, you want to make sure that the proportionality freezing point constant is indeed reported in degrees Celsius per molality. So that's the reason why we're using that unit. But again, just beware. You can always see different standards. So it just depends what it's calculated in. And so, of course, we like thinking about water since we can see it freeze. And so you can recall that pure water freezes at 0 degrees Celsius. And again, they're going to be in equilibrium, your ice liquid. And then salt disrupts that equilibrium, and it disrupts your packing structure. And so again, it dissolves in water and does not easily attach to the ice. So sometimes you can use this as a method of purification, like freezing out solids. I'm not sure how effective it is, but it does kind of work. And so when your solution has some dissolved solid, then that kind of freezes more slowly, and the ice that forms, again, would not contain much of the solute. So that just is saying, right, it's forming the crystal structure and then kind of pushing out whatever is in solution. But again, it can still form around it. That's why you lower the temperature, so it can still freeze around whatever's disrupting it. And so to return to our frozen equilibrium, our temperature must be lowered to make our water molecules slow down. And so on an exam, you'd probably have to be given this information. So I would give you your KF, so for freezing, and then you can look at where we're going. So we'll look at our boiling constant. And so again, this is for your solvent, and then the normal freezing points are given, and then you would just subtract, right, to get your new lowered freezing point. So depending upon your concentration. And so freezing point depression, boiling point elevation. So like we mentioned, the boiling point of a solution is higher. So now same thing, so now we have kind of less of our solution particles. And so then we have to raise the temperature by our factor. And so just like before, watch those units. How I'll give it to you is in molality. And again, our proportionality constant for our boiling should be given in these units. But again, if you look on the internet or other resources, just double check those units. All right, so sorry. So I'll have you write down the question probably, and then I'll have to scroll back up so you can get the relevant information. But as you write down this question, look at what it's saying. So what is a freezing point of a 1.7 molal aqueous ethylene glycol solution? And then when you're ready, I'll scroll up to the chart of constants. All right, so we're trying to find freezing point of a 1.7 molal aqueous solution, and so we'll need this information. So how did this problem go? So what number did we need to grab from here? What solvent are we interested in? Water. So excellent. So that was the big thing to recognize. So aqueous water. So then we need this information. And so, right, we need to grab the relevant KF here. So 1.86. And we can also write down our normal freezing point. And so 1.86 is our KF. And that's degrees Celsius per molality. And so now we can just plug it into our formula. So our change in temperature is equal to, right, our KF. And they already gave us molality, so we don't need to calculate anything. So 1.86 times 1.7. So then we get a change in temperature of 3.162, right? Is that what everybody got? And then we have to subtract it, so from our normal boiling point, so 0 minus this to give us, right, about a negative 3.16 degrees Celsius. Okay, that's probably a good place to stop. So let's at least talk briefly about your lab. So your lab should be pretty fun. So it's a titration. And what I like is you'll be doing what I would call like a more accurate one. And so what do you know about sodium hydroxide? What's the problem with it? Why do you have to? Because if you look at your lab, you kind of have to do 2 titrations, right? It says you have to standardize it to figure out your molarity of NaOH, and then you get to use your standardized sodium hydroxide solution to figure out moles of citric acid. So why do you have to do that? Or water. Yeah, so sodium hydroxide is called hygroscopic. And so that means it's always leaching in water from the atmosphere. It basically looks kind of sweaty. Like if you put a little bead out and then you leave it out there, it'll turn all sweaty and like eventually dissolve. But the key is we can never measure this mass accurately. And so in lab, we'll learn how we standardize it. We'll do 1 set of titrations. And then once we get that perfect molarity, right, because basically the problem is even if you set out to make a 1 molar solution, it won't be perfectly 1 molar because we can't measure it. So then in lab, we'll look at how we use our KHP to kind of standardize it. And then we'll, of course, figure out our citric acid. All right, I'll let you guys go for now. Stop talking. So we'll look at this more in lab. So just be prepared for a lot of titrations. I'll stop this.